Hello everyone, this is Mr. 13 Things and welcome to we40kids.com's discussion of and call it proselytizing for 4D mathematics, four-dimensional mathematics. Also known as quaternions. Also known as Hamiltonian numbers. Hamiltonian, not Eltonian numbers. And what I like to think of it is the math of satellites and robots. Now, ostensibly, this is my little attempt at getting folk to see that this concept of lattice mathematics, I like that, lattice mathematics, with a little bit of tweaking, ties our kids into their future and not our past. And put that in context, I think it was 57, I'll be wrong on that, when the first satellite went up into the sky. And I'm not sure about the first robot. So this goes from science fiction to reality, and it comes about by the use of four-dimensional math. I'll put a link here to those flying robots from TED this year playing the James Bond theme, and let you know that sometimes you take 15-dimensional math down to four-dimensional math, and then four-dimensional math doesn't sound so bad. And what has it done? It's basically used for a number of things, but basically combining rotation. So we're going to go through this simple process of showing, in effect, tying it to a link. I'll also put here a little kind of little code snippet that's posted out in Khan Academy that I'm working on that kind of does this justification a little more palatably, I guess, in terms of how lattice mathematics turns into four-dimensional rotation. So the problem that we're trying to get around is we're trying to get around of something called Gimbal Lock. Gimbal Lock. Now, okay, so we don't want Gimbal Lock. And it comes about when you're kind of doing rotation about three axes, and then one thing gets in the other, and you can no longer mathematically rotate. So you get around that by dealing with the mathematics, four dimensions. When we talk about four-dimensional math, what we're really in the end talking about is dealing with a real portion and then a vector that has three components. Okay, and these three components turn out to have their roots back to the imaginary number I, j, and k, where I squared equals -1, j squared equals -1, and k squared equals -1. But also I, j, k equals -1. And if you thought e to the I pi blows your mind, then this can blow your mind even more. But it works. By using this, multiplying two quaternions together in something called the sandwich product, we'll see why in a little bit, sandwich product, you can basically get to the point of doing pretty complex rotations relatively simply. And then eventually combining complex rotations, for instance, the sun around the Earth and the moon around the Earth and maybe the satellite of a Apollo spacecraft multiplying around the moon. So combining quaternions is something that makes it important to understand how to do a basic quaternion rotation. So the idea of the sandwich product we'll pick up in a second. We'll talk about a couple discussion points here before we move on. All right, so what each quaternion is going to be expressed either as four numbers, a real I, j, k, or a real number and then a vector. Right, and that vector is going to be a three-dimensional number. With the real number, that becomes three-dimensional vector, so that means a four-dimensional if you want. Think about it as a vector that way. And what you're going to be doing is you're going to multiplying a quaternion times a point taking that product and then multiplying it by the conjugate of the quaternion. And the conjugate, you'll find out when it's a complex number, the conjugate of 1 plus I is 1 minus I. But the conjugate of 1 plus a vector is 1 minus a vector in this case. So in other words, if this is a vector 3i plus 4i plus 5i, the conjugate is minus 3i minus 4i minus 5i. All right, so we're going to be looking at the sandwich product. So what I'm going to do here is something we don't like to do too often, but we're going to go ahead and just go ahead and erase all this. Edit, cut. And we'll talk about how these quaternions are defined. First off, let's talk about how the point's defined. So you have a point in 3D space. 3D space, of course, is going to require that you've defined your coordinate system. Which means you have an origin, a plus x direction, and then an up direction, which is typically z. And I'll post a video out here that shows you how you basically, this is the best way to think about it, put your fist basically at the origin, point your pointer finger to the x direction, put your thumb in the z direction, and then your cocked expressive finger becomes the y. So this is what, when I talk about having a point in 3D space. And let's, for grins, think about that point being someplace on a globe in a little bit. So that's one thing we're going to have, that's the point. The other thing we're going to want to do is talk about the Quaternion of Rotation. So Quaternion. The Rotation Quaternion. And that's going to be defined effectively. What goes into that is the axis of spin and then the angle of spin. The axis of spin is going to be a unit vector, vector of length 1, and the angle of spin we're going to call alpha, which is going to be in a positive counterclockwise direction. All right, so how do you define the quaternion? The quaternion, to do a spin, right, about this axis of spin and this angle of spin, is going to be the real portion. The real portion is going to be the cosine of the turn angle divided by 2. Okay, easy enough. And then the vector portion, which is the three-dimensional imaginary vector, is going to be the sine of alpha over 2 times the unit vector of the axis of spin. So the real port, again, this is the quaternion for rotation. Oh, edit, undo. This is what it's going to be. It's going to be comprised of that. And you can either think of that as either 4 components or a real component and a three-dimensional imaginary component. That's how you get the quaternion for rotation. For the point, basically the real portion is going to be equal to 0. I know that. Take that, undo. I believe it makes no difference what you put in the, but the real portion is 0, okay? And then the vector is basically the x-coordinate, the y-coordinate, and the z-coordinate. So you have basically a 4-dimensional vector. All right, so now let's just look at, and we'll stop at that, how do you do the first multiplication? So remember, this is a sandwich product. So you're going to take this first quaternion and multiply it by the point. So I'm going to do that, and here's where it comes in by making a grid where I've got the real portion and then the I, the J, and the K of the quaternion. And I'm going to multiply by the real portion I, J, K of the point. And this is where I'm going to try to do a better job. Now we come to that, what we were teaching the kids in 3rd and 4th grade. That we split this number up not into tens and ones and hundreds, but into basically fundamentally 3 different numbers that we can now multiply by a real times a real to get a real times an I to get an I direction, a real times a J to get a J direction, a real times a K to get a K direction. That's the easy one. Or real times I is I, and real times J is J, and real times K is here. Or real times real times I. Am I doing this right? Real I, J, K, real I, J, K. I was wrong in this. I times I is also a real. J times J is also a real, and K times K is also a real. So you kind of fill all these things in, and what comes out basically is another quaternion. Now, what doesn't exist here is all those crazy diagonal numbers, and I think we can maybe start to agree on it complexifies a really important concept of breaking a number up into its individual constituents when you put those crazy chutes and ladders down the diagonals. And so either adding a step or always showing the importance that you don't always have to kind of put these crazy chutes and ladders to really think about breaking a number up into its components and doing the multiplication. All right. So in the next video, we'll come back and actually do a calculation of how you figure out what the axis is, and then from that axis come up with a quaternion based on a particular spin. And remember, we don't want to forget that this is alpha over 2. The way this works is kind of interesting, fascinating, and I can't say that I understand it. But this is how you get a robot arm to kind of figure out exactly where to go from one spot to another. That's the best way I guess I can describe it. So we're going to describe the quaternion by the cosine of alpha over 2 as the real portion, and the imaginary portion being a 3-dimensional vector that is the sine of alpha over 2 times the unit vector of the axis of spin. That's the quaternion of the rotation. The point will be described by 0, kind of odd how that works that way, and then x, y, and z will be the imaginary components in the I, J, and K direction. And that kind of goes along with convention of the unit vector in the I, J, and K directions. Those things together will get us to the point where we can do 4-dimensional math by learning to use the lattice method. And finally, I'll take you out to basically a basic function in Ruby that shows you probably will never do that once you understand how it's going on, because basically it's been programmed anyway. Thanks for listening.